Welcome to today's video. Today we're going to solve two exercises related to special relativity and particle dynamics. I hope that these two exercises are fun, they teach us something new, and also gives you an idea of the kind of exercises that you could be asked to solve in a hypothetical assignment about this block. All right, let's see. Consider a scenario where we have a total energy budget E to accelerate two particles. You can distribute it between the two particles. And this is a particle collider exercise. So imagine that you are in charge of designing the new LHC, and you have two options. You have an energy budget E, and you have to decide how to split the energy budget. You can either use all the energy to accelerate one particle, or you can use half of the energy to accelerate one particle and the other half to accelerate the other in a collision. So this one would be in the scenario B. The particle that is accelerated moves towards a particle that is stationary, is at rest actually, in the lab frame. And in the other one, the two are accelerated in the lab frame, one against the other. And again, E over 2 energy to each of them. So the energy is split equally. Well, the question is, which one of these two scenarios is better in order to maximize the center of mass energy? Now, the center of mass energy is the important bit. When you hear the LH3 can reach this amount of energy, they talk about center of mass energy. And that means not the energy of the center of mass, but the energy in the center of mass frame. The energy in the center of mass frame is what produces all those jets and all those particles that you want to detect at the LHC. That's the real energy in the collision, if you want. Now, it may be counterintuitive. Maybe some of you are thinking, hold on, but it's the same amount of energy in both cases, right? This is a budget energy E in the lab frame, and I can split it in two particles accelerated, or in one. It should be the same. Now remember that energy is a frame-dependent notion. So we have to be really careful when we say we have an energy of, I don't know, 20 tera-electron volts of something like for the collision. You know, it depends on what reference frame you're talking about. And in particular, the one that we want to maximize is the energy in the center of mass frame. Now, again, we have energy E in the lab frame to distribute between the two particles by accelerating them. And you may be thinking, but shouldn't it be the same? It's the same energy in both cases, right? E. Well, maybe that intuition is coming from Galilean physics, from non-relativistic physics. And we will see. Perhaps in the non-relativistic scenario, both scenarios are the same, both cases are the same. But in the case that we take into account relativistic effects, they're definitely not the same. We'll see. Now, the question I ask is which scenario maximizes the center of mass energy, which again, I mean by that the energy as measured in the center of mass frame. So the energy is, if you want, containing the two particles, but as seen in the center of mass frame. Okay, and then I asked you also to compute the ratio between the center of mass energies in both scenarios. So which I just don't want a number for each, I want one over the other to see how much better one is over the other. And finally, I asked you to evaluate the ultra-relativistic limit for that ratio and the deep non-relativistic limit. That is when the energy is high, when the energy that we put into the particles is really large, and this is the ultra-relativistic limit, so the particle becomes really, really, really relativistic, and the other one is the deep non-relativistic limit, when the particles have very little energy in the lab frame, which is going to be the Galilean limit, right? Okay, well, let's see what the answer to this, I think it's an interesting question. Let's see what the answer is. All right, let's consider first scenario. The energy in the lab frame, capital E, is equally split between the particles. And I call this letter calligraphic E, capital E over 2, just for having an easier handle of it and knowing, okay, this calligraphic E is the energy that we actually impart into each of the particles. Now, in the lab frame, we see that we pick a sign for the direction of X, and we see that the particle 1 has momentum P, particle 2 has momentum minus P. We're going to make them collide. So it's very easy to write the form momentum. Before we write it, remember that these particles have a rest energy, of course, of mc squared. That is always there. Mc squared is the rest energy, the energy in their rest in the proper frames, if you want. It is very easy to build the form momentum for each particle in the lab frame. Now, the first thing to remember is that in an arbitrary frame, the form momentum you can write as, of course, the energy that the particle has in that frame divided by c, and the tri-momentum that particle has. All right, so with this, it's very easy to build now the form momentum of the two particles in that frame. So let's say particle 1 in the lab frame, and we notate it like that. What is the energy that we have? Well, we had the rest energy that we had at the beginning, And we also have the energy calligraphic E that we added. So the rest, all that energy divided by C, this would be mc plus epsilon, or sorry, E divided by C. What about the spatial components? Well, in the lab frame we can choose the x-axis to be the collinear axis, the axis that joins the two particles colliding, and then we know that there's only x component, right? So this would be the form momentum in the lab frame for the first particle. Now for the second particle, it's very easy. In this scenario, for the second particle in the lab frame, we have that the energy is the same. We split it in half, so we have the same rest energy, they're identical particles, plus the energy that we put by accelerating the particle. And the tri momentum is of course the same in magnitude as the one we put in particle 1. We spend the same amount of energy accelerating, only directed in the opposite direction. So minus p 0, 0. Wonderful. So with this we can compute the total for momentum. Let's call it total in the lab frame, which is of course the sum of the form momentum of the first particle in the lab frame plus the sum of the form momentum of the second particle in the lab frame. And of course that gives me the 4 vector, so the component is twice mc plus 2 calligraphic E divided by C. And this is 0, 0, and 0. Now of course, as we mentioned before, if we don't need to change to the center of mass frame, because this is already the form momentum in the center of mass frame. Because the total tri momentum, you see, is 0, and the center of mass frame is precisely the frame in which the total tri momentum is 0. The total linear momentum is 0. So this is the same as P total Cm. All right. Also, this is the same as P1 Cm, and this is the same as P2 Cm. All right. Okay, so we know that this is P mu total Cm. Right. Now, of course, we know that the energy, if we want now, the energy for scenario A in the center of mass frame, that's going to be equal to C times P0 total in the center of mass frame. Now, we know what that is, just reading out from there. And this is, let me just get a common factor, 2mc squared outside. So we have 2mc squared that multiplies 1 plus calligraphic E divided by mc squared. And I can erase this, which is now in the way, and we don't need to use for now. All right, so this is the first result that we need. We have, let me collect it here, let me just automatically collect it here, like that. And you can tell that this is actually a very neat way of expressing it, because this is the energy in the center of mass frame, the total energy in the center of mass frame, expressed as the total rest energy that we have, multiplied by a factor larger than 1, and this factor is larger than 1 precisely by the ratio between the energy we spent in accelerating divided by the rest energy of each particle. So the energy that we spent in accelerating each particle divided by its rest energy. So a very neat way of presenting it. Now, this was easy. Let's now change to scenario B. So in scenario B, we spent all the energy in accelerating the first particle. So the second particle remains at rest in the lab frame, and the first particle is accelerated with a total energy E, which is equal to 2 calligraphic E. Okay, wonderful. So let's write the form momenta in the lab frame, which is always easy. So we have, for the first particle, the rest energy contribution plus the contribution of the energy you spent in accelerating it. So it would be 2 calligraphic E divided by C. And the tri momentum, well, I call it K, and again we choose the collinear direction to be the x-axis. So that would be K 0, 0. That's for the first particle. What about the second particle? Super easy. We only have the rest energy contribution and the 0 tri momentum for the second particle. Now we can build the total for momentum in the lab frame. So P mu total in the lab frame, which is of course the sum of P mu 1 in the lab frame plus P mu 2 in the lab frame, And that is equal to, if I write here, twice mc plus twice calligraphic key divided by c. Then we have k, 0, 0. All right. Now the difficulty here is that the lab frame is not the same as the central mass frame. In the central mass frame, remember the definition, the central mass frame is the frame at which the linear momentum is 0. And the total linear momentum is 0. And as you can see here, the total linear momentum here is k0, 0. So this is not the central mass frame. And remember that if I want E in scenario B in the central mass frame, I need C, P, 0 total in the central mass frame. And that I cannot get directly from that. I need to compute it. Okay, to compute this, we're going to have to proceed in steps. So the first step is determining K. We need to know what K is, the value of this strike momentum. We need to compute. So how do we determine K? All right, so I'm going to store here this in a kind of box to not mix with everything else. This is what we want to compute in the end. But first of all, determination of K. So first, find K. We can compute K in terms of the inputs of this exercise. How? Well, recall that the form momentum of, let's say, particle 1 in the lab frame, mu, contracted with itself, so the norm of the form momentum, as we saw in class, sub mu, is equal to minus m squared c squared. And we know that from the previous video. This is true for any form momentum of any particle. Wonderful. So we know that this expression, the contraction of p super mu, p sub mu for particle 1 is going to be minus m squared c squared. But we also can compute in the lab frame the left-hand side. So if we compute, let's say, p mu, p super mu, 1 lab, contracted with p sub mu, 1 lab, this is, well, we know that this is going to be minus p0, 1 lab square plus the vector p. In this case, will be only p1, but just write the vector p, 1 lab square. All right, let's substitute. Okay, and this is equal to, just looking at this is the p0 component. This is the spatial component, it's only one component that is k. So let's write first minus p0 square, minus that covers the square of this component. So that would be m squared c squared plus 4e squared divided by c squared plus 4 times m e. Wonderful. And of course we have now the square of the spatial part, which in this case is just plus k squared. And now we know that these two things have to be equal because it's the same magnitude. So we know that this is minus m squared c squared. Now this term cancels this term, and we can solve for k. So in this case we get that k, let me write it here, it's equal, now naively just writing here, is the square root of 4e squared divided by c squared plus 4me. But we can simplify this and write 2e divided by c as a common factor that I take out of the square roots, and that gives me 1 plus mc squared divided by e, which is kind of nice again to compare the two expressions. Wonderful. So we determined the value of k. Now we have the value of k. The next step is to try to determine this, the total zeroth component of the total momentum in the center of mass frame. Now there are two ways to computing this. One is the long and painful, which is, find the velocity, the relative velocity of the lab frame and the center of mass frame, find the lambda that transforms you from one to another, and they apply the lambda to the total force vector of total momentum in the lab, total force momentum in the lab, and transform into the center of mass frame and just check the zeroth component. That is the long and painful. This is the one that I would not recommend you to do, and actually is the one that when I give this exercise as assignment, most people do. There's a much better way. To actually do this better way of computing things, we need to recall that the total force momentum in the center of mass frame will only have zeroth component, because by definition, the spatial components of the center of mass frame total force momentum have to be 0. The center of mass frame is that for which the linear momentum is 0. The total linear momentum is 0. So the total time momentum is 0. Now, knowing that, we know that the contraction of the force momentum, total force momentum in the center of mass frame with itself will be just minus the zeroth component squared. That on the one hand. On the other hand, we know that this thing is Lorentz invariant. Why? Well, because it's a scalar. We have a 4-vector contracted with a 4-vector, 0 labels in the end out of the contraction of two 4 vectors. That means it's a scalar. That means that it's the same in all frames. Wonderful. Well, if it's the same in all frames, we can choose one frame to compute it. And the one frame in which we choose to compute it is the lab frame. I can compute it in the lab frame. So I'm going to use that P super mu total center of mass, P sub mu total center of mass is the same as P super mu total lab contracted with P total lab sub mu. It's a scalar, so it's the same in all reference frames, in the center of mass frame and in the lab frame. And in the lab frame I can compute it, because in the lab frame I have the total for momentum here, and I can compute the contraction. And once again, the contraction of this would be minus P0 total lab plus, well, square, plus P vector total lab square. And directly from here, I get that this is going to be minus, and I have here 4 times m squared c squared plus 4 times e squared c squared plus 8 times m e plus k squared. We have k in here. I wrote again the neat way in which we can write it by simplifying. Okay, so why don't we just substitute k and see what we get? So we see the calculation just substitute what we had before, substituting k squared from this expression gives me this, and then we can see how this first term actually cancels with the 1 in here, right? And it simplifies to this, which we can write in compact form as that. Okay, so to compute what we want now, which is E in case B in the center of mass frame, to compute that quantity, then again, going back to this, is C, 0th component of the total for momentum of the center of mass, which is of course equals to C
square root of minus P mu total center of mass, P total center of mass mu.
And because again, this is the same in all frames, we computed with the lab one, but we know that it's the same in the center of mass and in the lab, so we can substitute by this result that we obtained. This is going to be equal to twice mc squared, already multiplying by the c, square root of 1 plus e divided by mc squared. And this is the second result we want. We want e be center of mass. This is 2mc squared. So same as before, is the total rest energy multiplied by a factor, which is larger than 1, which is the square root of 1 plus the total energy imparted, well, half in this case of the total energy imparted, divided by mc squared. All right, so now we're in conditions to compare them and see what happens in the ultra-relativistic limit and in the deep non-relativistic limit. Let me erase everything. So we have here the ratio between the two scenarios, the energy, the center of mass energy in the two scenarios. Now, you can tell here by the expression that results, doing the ratio between the two results obtained, is that is the square root of 1 plus the ratio between calligraphic E and the rest mass of one particle. And this thing is always larger than 1, which means that scenario A always wins. It's much better if you're going to design a collider to accelerate both particles, spend the energy equally between the two particles. That's the optimal case, actually. And if you consider only accelerating one of them, that's always going to be at a disadvantage. Now, this is why you will see particle colliders where they accelerate both jets that are going to collide, both particles, if you want, that they're going to collide. Now, you can tell, we can take two limits in here. Now, these limits are slightly tricky to take. I mean, not much, but one needs to think a little bit about the notions that we learned in the previous video. If we take the deep non-relativistic limit, that means that mc squared is much larger than pc. All right, from the previous video as well, we know that for each particle, let's go to the case that we give calligraphic E energy to each particle. So that's the case in which we accelerate both. In that case, we know that that limit would imply that because the total energy for each particle is always m squared c to the 4 plus p squared c squared square roots, then we know that this has to be equal to the total energy in the scenario that we're considering for each particle. Now, in the limit that mc squared is much larger than pc, that means that this E has to be very close to 0 for these two sides to be equal. All right, then we can conclude that in that limit, the ratio goes to 1, because if this E goes to 0, this ratio is getting closer to 1. Which makes sense, because that is telling you that in the Galilean limit, if you don't use relativity and use mechanics pre-relativity, then you would conclude that it doesn't matter. If you have energy, just put it whichever way you want, that's the energy you're going to have in the collision. However, we know from here that this is only true in the non-relativistic limit, in the deep non-relativistic limit. What happens in the ultra-relativistic limit? Well, a similar argument in the ultra-relativistic limit says that, if Pc has to be much larger than mc squared, that means that E has to be basically Pc, because if that's the case, then Pc is much larger than mc squared, then Pc is larger than mc squared here inside the square root, and you neglect it on the left, you neglect it on the right, and you get that roughly E has to go like Pc, and that means that the ratio has to go like square root of 1 plus Pc divided by mc squared, which is something that goes to infinity actually. So in the ultra-relativistic limit, the closer you are to accelerating these things to the speed of light, the more different the two scenarios would be. You can actually wave your hands around it, and this is usually the way when you get a first contact to particle physics, the way it's explained. It's by saying, well, the faster is a particle in my frame, the more energy in my frame would cost me to accelerate it. So better keep the velocities as low as you can as you accelerate them. That's kind of the waving hands arguments around it. Of course, hand wavy arguments are not satisfactory. Here is out of a calculation, and you can tell. The more relativistic you get, the higher this thing will be, and actually it will, in the ultra-relativistic limit, in the limit that we're really, really close to the speed of light for both particles, it would actually be divergent. Now, of course, I took the case where each particle has an energy epsilon. We could have done the same with a 2 in here, with a 2 in here, and that would be 2 in here, and then a 2 in here, and the conclusion would be the same. These limits are taken, remember that these limits are limits when one term is negligible with respect to the other. It's not telling you the exact value at every time as you get close to the limit, but tells you what the limit is asymptotically. All right, so this is the solution to this exercise. Now you know that if you want to accelerate two particles, without any approximations in neither of these limits, you know that always it's better to put energy distributed equally between the two particles you want to accelerate to make them collide. If you want to maximize the center of mass energy, which is the one that will give you your new particles, if you want to find it, your Higgs boson, or your out of the standard model things that you want to get. And we know also that in the non-relativistic case, it doesn't matter, but if you have to accelerate them enough to be close to the speed of light, you better accelerate both equally and not put all the energy in one. All right, let's see another exercise. All right, so the text of question 2 is just the first line in here. Show that an ultra-relativistic particle, that means that if the tri-momentum of that particle is k, mc squared is much larger than kc, where capital M is the mass of that particle, cannot break into two identical mass particles of mass that are much larger than the mass of the particle they split from. This is an impossible feat, and I want you to prove it. Now, the one thing to keep in mind here is that this scenario is not very weird. This scenario would be the same as saying, show, the most ultra-relativistic case you can think of, show that a photon cannot split into a positron and an electron that have identical mass, by the way. So, a photon cannot split into an electron and a positron. They have identical mass, and it's definitely much larger than the mass of the photon, which is exactly 0 in that case. So we need to prove that a photon will never be able to disintegrate into an electron and a positron. And that is something that we will prove. It's a positron. You may be surprised by this, because in popular science, of the time people say, oh yeah, from a photon you can create a pair electron positron. Well, that's not true. You need something else to participate in the collision, otherwise it's impossible. Okay? And if you have questions about that, please ask me in the live session. For now, let's just prove that it's impossible. All right, I wrote here the form momentum, the contraction of the form momentum of the particle with itself, and then of the two particles that split, I wrote also the contraction of the form momenta of each particle with the form momentum of each particle with itself. And here I wrote the contraction of form momentum of the particle 1 with the form momentum of particle 2. Anyway, let's talk a little bit about what all this means. Now, I wrote here that this is of course minus m squared c squared, and there's a bit of an abuse because it's not that the mass, well, in the case of the photon, this would be an equal sign. But we're not saying in the question that we're limited to the case of a photon into two positrons, right? Into a pair of positron electron. Instead, what we're saying is that the mass is much more than the momentum of the particle that comes, and we also say that the masses of the two particles that split out are much larger than the mass of the original particle. But I write here, this is an abuse in like this is going to be neglected, but it's going to be neglected only in a sum when you have terms that are much larger, right? Like the four momenta of the total particle or the masses of the ones that break off. Of course, let me remind you, this would be exactly an equal sign in the case of the photon into an electron-positron pair. All right, now this we got from the previous video, right? We know that the norm of the four momentum is this one for a particle, and we know that the two particles have identical mass, they're identical particles, so we get that this expression is true for both four momenta. And I computed here the contraction of P1 and P2, remembering from, again, the previous video, that P1 mu can be written like that, where E1 is the energy that the first particle gets out of the collision of the split, and P1 is tri-momentum, is linear momentum, and same for P2. So if you compute the contraction of the two, you get minus 1 over c squared, so the product of the zero of components with a minus coming from the metric, and the dot product of the tri-momenta. All right, so all that we need to do now is write the equation of conservation of four momentum. Let's write it. So this is the implication of the conservation of four momentum. So is four momentum conserved here? Well, let's ask Nether. Is the setting translational invariant in time and space? And the answer is yes, the laws of physics will be the same if the collision happens here or if the collision happens here. The whole thing is invariant under translation. There's no potential out there that makes the thing be different depending on where I put it. It's just one big particle split in two. So this is translational invariant. Is it also time invariant in any frame? Sure, it is time invariant. If I wait if I start the process in 5 minutes, it will be the same process as if I start it now. It is time translational invariant as well. All right, so that means, according to Nether's theorem, as we saw in the previous video, that means, or 2 videos ago, if you want, that means that four momentum is conserved. That means that the four momentum before the collision, K nu, it's equal to the sum of the four momenta, the total four momenta after the collision. And again, this will be true in any frame. It's conservation of four momentum coming from Nether's theorem. Wonderful. So what does that imply? Well, in particular, let's just write a quantity that is going to be on top of being a conserved quantity before and after the collision, would be a Lorentz invariant, which means the same in all reference frame. That is the contraction of K mu with itself. So let's contract K mu with itself. And this is equal to two things. On the one hand, we know it's going to be equal to minus m squared c squared, right? So on the left hand side, so I'm going to have this thing is going to be equal to minus m squared c squared. And on the right hand side, this thing is going to be equal to, well, split it in two. This thing is going to be P1 mu plus P2 mu contracted with P1 mu plus P2 mu. All right, so what is this? This is going to be P1 mu plus P2 mu, P2 mu plus twice P1 mu, P2 mu. All right, because of course we know that P1 mu, P2 mu is equal to P2 mu, P2 mu. Wonderful. So we can substitute the values of these things that we already computed in here and write them here. So let's write the first term. That's going to be, the first and the second term is minus m squared c squared. So minus 2 m squared c squared. And then I write the other term, plus or minus, I'm going to write here.
Minus 2 over c squared, E1, E2, plus 2, P1 dot P2.
All right. So the first thing to realize now is that now we can neglect this thing is negligible as compared to this one. So we can now effectively make this zero. This is approximately zero. Let's write it like this. Approximately zero. Because now it's in a sum with something that is much larger than it. Okay, wonderful. Now, next step. So we just separated, we isolated for P1, P2 and obtained this relationship because this thing is negligible as compared to that one, obtain this relationship. And this relationship is very interesting because we get the following. We get that m squared c squared plus E1, E2 divided by c squared is equal to the dot product of P1, P2. And what is that? Well, that's the modulus of P1, modulus of P2, cosine of the angle, let's call it theta, between the two particles that split off. The nice thing about it is that this is always less or equal than P1 times P2. So we obtain one interesting result. So this implies that m squared c squared plus E1 E2 divided by c squared is less or equal than P1 times P2. Interesting. So this is our result. Now, okay, so this is just telling me some constraint between the momenta and the energies and the mass of the particles, but that doesn't mean it's impossible. Yes, but we also have other equalities. You may have noticed that at some point in the previous sentences, I substituted the formulas that we already used by these ones. Now, what do they say, this one? Well, this one comes from the previous video. And the previous video, we had that the energy of each particle would be equal to the square root to m squared c to the 4 plus p squared c squared. We can apply it to, we can solve for p in this expression, we can isolate p squared or p, right? And then obtain that the form momentum would be equal to the square root of energy squared divided by c squared minus m squared c to the 4. Now we do it for each of the particles that split off here, and we find that indeed P1 is this expression here, so it's the energy divided by c squared, energy divided by c all squared minus m squared c to the 4. But notice that this quantity is positive, this quantity is also positive, so this thing is always less or equal than E1 divided by c. And the same applies for particle 2. Interesting. If we combine this with this, we obtain, let's see, what does that mean? Well, that means, let me write it here, that P1 times P2 in magnitude would be less or equal from this thing, E1, E2 divided by c squared. But on the other hand, I have that this thing has to be larger or equal than m squared c squared plus E1, E2 c squared. Well, that's a bit of a problem because you can tell here that this thing cannot be the only possibility. This thing is positive. This thing is positive. So this will always be larger or equal than this thing. The only possibility is that this term were 0 and then everything would saturate the equality. But this thing is not 0. This thing is a finite mass. What the particles that break out have a finite mass. And therefore, this condition is impossible to fulfill. When I write it, impossible. Impossible since m larger than 0. Alright, so that means that this process cannot occur if the form momentum has to be conserved, which it has to be because this process is invariant under time translations and spatial translations. So, we just proved that an ultra-relativistic particle cannot break into two identical mass particles. And this applies certainly to the case of a photon splitting into an electron and positron. That is impossible, and we just proved it. Alright, so these are the two exercises I wanted to do today. Next video, we're going to start the last part of the block, which is non-inertial reference frames and the Riemann metric. Until then, take care.